Hello everyone, and welcome to today's chem lesson. Today, we are going to talk about balancing equations. Now, when we've looked at equations in the past, we really haven't thought about this piece, right? Whether or not they're balanced, because it hasn't mattered to us yet. But now, as we move forward and do more chem, we are going to need equations to be balanced. And what this means is that we are following the law of conservation of mass. Conservation of mass, if you don't remember, says that mass cannot be created or destroyed. It can only change forms. And so that means when we have an equation, like this for example, we can't make new atoms, we can't destroy atoms. We need to have the exact same number of atoms of each type on the left side of the arrow and on the right side of the arrow. So see, this equation is not balanced. There's one carbon on the left, one carbon on the right, one oxygen on the left, but two oxygens on the right. So in this situation, if we read this literally, we have created a brand new oxygen atom. And that is not something that we have the power to do. We can't just make atoms. So we need to adjust. We need to have this be balanced. We need to put a 2 here so that we have one carbon and two oxygens on the left and one carbon and two oxygens on the right. And that's our job. Our job when we balance equations is to put coefficients in front of whatever is given to us to make sure that we get the same number of each atom on the left and on the right. So, let's look at a more complicated example. Here we have an unbalanced equation. We've got 2 moles of carbon on the left, 1 mole of carbon on the right. 4 moles of hydrogen on the left, 2 moles of hydrogen on the right. 2 moles of oxygen on the left, 3 total moles of oxygen on the right. So not a single piece, not a single element is balanced here. We need to put numbers into these spots to make sure that everything balances out, that we have the same amount of each thing on the left and on the right. And now, how do we do that the most effective way, right? What do we need to do to make this efficiently balanced? The way I like to do it is I like to write what is in each thing with pencil underneath and then update that number as we balance. Right, I like to take apart each element, or each compound, apologies, into its elements. Right, C2H4, that's 2 C's and 4 H's. O2, that's 2 O's. H2O, 2 H's, 1 O. And I also like to put a little marker here just to remind me where my left and my right is. So that looks something like this. Now, when you want to start balancing, really it's a trial and error. You can start anywhere. You can pick any one of these things to start with, but the thing that will give you the least amount of work, the thing that will make it the easiest to balance an equation, is always starting with the biggest thing. Now, what do I mean by biggest thing? I mean the one with the most atoms in it. Here, carbon dioxide, that has 3, right? 1 carbon, 2 oxygens, right? There's 3 atoms in it. Same thing with water. 2 H's, 1 O, that's 3 atoms. O2, that's 2 atoms. C2H4, that's 6 atoms. That's going to be our biggest thing. And so I am going to start by putting a 1 in front of the C2H4. Putting a 1 in front of my biggest thing. Now, is that going to work every time? No, but it will give you the least amount of work. So, I put a 1 in front of the C2H4, and that solidifies, for me right now, 2 C's and 4 H's. I need to adjust the other side so that I get 2 C's and 4 H's. Because right now I've got 2 H's and 1 C, and that's just not balanced. How am I going to balance the other side? What numbers am I going to put in front of the H2O and the CO2 to give me 4 H's and 2 C's? How many H2O's do I need to get 4 H's? And how many CO2's do I need to get 2 C's? In this case, we're looking at a 2 for each of them. 2 H2O's is going to double my numbers here. I'm going to get 4 and 2. 2 CO2's is going to double my numbers here. I'm going to get 2 and 4. Alright, so putting those 2's in means that now my hydrogens are balanced. Now my carbons are balanced. Or I've got the same number of C's on the left and right, same number of H's on the left and right. So far, so good. But now, I need to sit and focus in on my oxygens. When I look at my oxygens, I've got 6 on the right, but only 2 on the left. And so I now need to put a coefficient in here that's going to bring this number of oxygens up to 6. What coefficient is going to bring this number of oxygens up to 6? How many copies of O2 do I need to get 6 oxygens? Here I'm going to need 3 oxygens. 3 copies of O2, right, it's a multiplication, it's going to bring me to 6. And now, my equation is balanced. 2 carbons on the left, 2 carbons on the right. 4 oxygens on the left, 4 oxygens on the right. 4 hydrogens and 4 hydrogens, 6 oxygens and 6 oxygens. And I've got the same number of each atom on the left and on the right. And that is the most important thing. That is what we're trying to do. Now, like I said, you can start anywhere. You don't have to start with the biggest thing. If we started with CO2 or H2O, we just would have had a little bit more work to do. If we started with a 1 in front of the H2O, we would have found out that that doesn't work. Because 1 H2O means 2 H's, but I can get a minimum of 4 H's at a time here. So this immediately needs to go back and be changed to a 2. Right? If something doesn't work when you're balancing an equation, you just go back and you change the number, right? If we found that this 1 didn't work, we would stop, erase our coefficients, and make this a 2, and then work from there. And if that 2 doesn't work, we would go back and stop and erase and make it a 3, and go and plug around with a 3. starting with the biggest number, or the biggest compound, is always going to get you the least amount of work. Now, let's take a look at balancing some equations on our own. Sometimes, equations start balanced. It's not often, but it does happen. This first equation is balanced already with a 1, a 1, and a 1. I wanted to point this out because it does happen, but again, it is not something that happens very often. Now, I'm going to give you about a minute, minute and a half to pick some of these and try to balance them on your own. Remember, please pause if you need more time. When we look at the answers to these questions, we are going to get something that looks like this when everything is balanced out. Like I said, this first one started off balanced with 1, 1, 1. Just like in every other aspect of chemistry, you do not need to write a 1. Right? Ones are assumed. But none of the other ones started balanced. Now, an interesting point came up in the chat. Right, Kyle asks, can we ever have a half? Right, if I wanted to balance this, could I do H2 plus 1 half? O2 makes H2O 1, 1. And the answer is no. You always need whole numbers. The definition of a balanced equation uses the smallest whole number ratios. Alright, balancing the equation requires the smallest whole number ratio. Which means this, even though it is balanced, is not good because of this 1 half. If you notice this in the beginning, you say, okay, this makes it balanced. There's a very easy way to then take this and make it a balanced equation. And that's just doubling all your pieces. Doubling all 3 of these numbers brings you to 2, 1, and to 2, which is the right answer. But attempting to put in decimals, right, 0.5 or 1/3, it's not a thing that you are allowed to do. have another set of practice problems here. I want you to try anything that's not the first one. I would like to do the first one with you. Actually, we're going to do the first one together, and then I'm going to let you try the rest. All right, when we look at the first equation here, FeCl3 plus NH4OH. And then I messed it up. When we look at this equation, there's a lot going on. But one of the things that you might notice right off the bat is this OH in parentheses with a 3. When you see something like this, when you see something in parentheses like this, you know, because we spent a lot of time doing balancing or doing ionic compounds, that this is a polyatomic ion. And now a little trick that you can use is, instead of taking this whole thing apart and saying 1 iron, 3 oxygens, and 3 hydrogens, if you can spot the polyatomic ion on the other side, oh, there it is, you can actually leave the polyatomic ion together and treat it like a clump, like it is. You can say this is 1 iron and 3 hydroxides. Same thing goes for this NH4, which is a little harder to spot, but is still a polyatomic ion. You can say this is 1 NH4 and 1 chlorine. Here you have a 1 NH4 and 1 hydroxide. 1 iron, 3 chlorines. And this actually cleans up the whole process a little bit. Instead of now trying to balance the H's separately, you see that OH is together no matter where it is in the equation. NH4 is together no matter where it is in the equation. And now we can go about balancing this. Like I said before, you want to start with the biggest thing, the one with the most atoms in it. In this case, NH4OH is the one with the most atoms in it. So if we start with a 1 there, we immediately go back and say, okay, I got 1 OH, but I have 3 on this side. So that means the minimum number of NH4OHs I need is going to be 3. Because if I want the left to equal, I can't make this smaller. If I want the left to equal the right, I need to make this number bigger. So, 1 doesn't work. 2 doesn't work for that same reason. 3, though, that's going to give me a 3 and a 3 here. My OHs are balanced. NH4s, I got 3 NH4s. I need to go here and put a 3, giving me 3 NH4s and 3 Cls. And then, believe it or not, I'm balanced. A 1 here and a 1 here. 1 iron on both sides, 3 chlorines on both sides, 3 NH4s on both sides, 3 OHs on both sides. Treating polyatomics as the clumps that they are, where you can, is going to save you some time. Right, another important one is down here. You can treat the SO4 like a clump, but the OH, not so much. Right, the OHs don't stay OHs, they become H2O, so you should take this one apart to get O's and H's, but SO4 is together on both sides. Right. Now I'm going to give you another minute and a half, 2 minutes to try to balance some of these equations. Remember, pause if you need more time. look at these equations and we get them all balanced, they look something like this. Correctly balanced out, these are our coefficients. Remember, for a balanced equation, you want the smallest whole number ratio. Right? So that means no halves, no decimals. And if you see something that, like, if you got 4, 4, and 6, you should be able to reduce that down to 2, 2, and 3. Smallest whole number ratios. And with that, I'm actually going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. I will see you there.